we are going to become clinical detectives. We're going to see how just a few simple numbers from a patient's blood can tell us this incredible story about a life or death struggle happening inside their body.
So, what if I told you that you could solve a major medical mystery with just 3 little numbers? I know, it sounds like something straight out of a detective show, right? But it's a real-life, incredibly powerful diagnostic tool. And today, you're going to learn exactly how to use it. So, what's the mystery we're tackling? It's the body's super delicate acid-base balance. You can think of it like a constant tightrope walk between being perfectly healthy and being in a real crisis. And our magnifying glass, the tool we're using to peer into the bloodstream, is the arterial blood gas analysis, or ABG for short. Okay, so every good detective needs to know what clues to look for, right? Well, in our case, it all boils down to 3 key numbers. Let's dive in and decode them. Our first, and you could say most important clue, is the pH. This number gives us the big picture, the overall state of the blood. Is it too acidic or is it too alkaline? This is our starting point, our very first impression of the crime scene. Next up, we've got PCO2. That stands for the partial pressure of carbon dioxide. Now, since our lungs manage CO2 by breathing, this value points directly to the respiratory system. If this number is out of whack, the lungs become our #1 suspect. And our third and final core clue is HCO3, which is bicarbonate. This is a base, and it's managed by the kidneys. That makes it our metabolic suspect. So if this number is the culprit, our investigation immediately pivots towards a metabolic problem. So these right here are the numbers for a normal scene of the crime, when everything is in perfect balance. A pH between 7.35 and 7.45, a PCO2 between 35 and 45, and bicarbonate between 22 and 27. You really got to know these numbers, because as a detective, you have to know what normal looks like before you can ever hope to spot what's wrong. So here's the bottom line. When things go haywire, it's really one of two main problems. If that pH drops below 7.35, the blood is too acidic. We call that acidosis. But if it climbs above 7.45, it's too alkaline, and that's alkalosis. See? Simple as that. Okay, so we know the clues we're hunting for. But, a detective is only as good as their evidence. So how do we actually go about collecting it? And listen. Getting this evidence has to be done just right. The blood must come from an artery, not a vein. A venous sample just won't cut it. Usually, we go for the radial artery, right there in the wrist. And the sample gets collected in a special heparinized syringe, which is just a fancy way of saying it has a coating that stops the blood from clotting before we can analyze all those clues inside. But wait, before we even think about taking that sample, there is an absolutely vital safety check we have to do. I mean, how can we be sure the hand will still get enough blood if something goes wrong with that artery during the procedure? Well, the answer is a really simple but clever procedure called the Allen test. First, you press down firmly on both arteries in the wrist while the patient makes a fist over and over. This forces the blood out and the hand turns pale. Then you let go of the ulnar artery only. If you see that color rush right back into the hand, you know that one artery is strong enough to supply the whole hand by itself. That's our green light. It's safe to proceed. All right, with our evidence safely in hand, the real investigation begins. We're now officially on the hunt for one of 4 main culprits. This chart, this is our master key. Seriously, just look at the pattern. For any respiratory problem, the pH and the PCO2 move in opposite directions. For metabolic problems, the pH and the bicarbonate move in equal directions. If you remember one thing, remember this. Respiratory opposite, metabolic equal. That's really the core of the whole diagnosis. But hold on, the story has a little twist. You see, the body is smart. When one system starts to fail, the other one doesn't just sit on the sidelines, it actually tries to help out. This is called compensation, and it adds a whole new layer to our investigation. The easiest way to think about compensation is to picture the respiratory and metabolic systems as best friends. It makes sense, right? If one of them gets sick, the other one isn't going to be happy. It's going to jump in and try to fix things. So when a problem is uncompensated, it basically means the healthy friend hasn't gotten the news yet that something is wrong. The system that isn't causing the problem, its values are still completely normal. For them, it's just business as usual. Now, in a partially compensated state, the friend has arrived on the scene and is actively trying to help. So now, the system that isn't the primary cause shows an abnormal value. It's working overtime to fix the balance. The key here, though, is that it hasn't quite succeeded yet. The overall pH is still outside that normal range. And finally, we have fully compensated. This is when the friends' hard work pays off. Their efforts have successfully brought the pH back into the normal range. But our investigation isn't over. Even though the pH looks normal, the other values are still off, which tells us there's still a struggle happening just beneath the surface.
All right, detective. You know the clues, you've met the suspects, and you even understand the plot twists. I think it's time we solve a case.
Okay, here's the evidence straight from the lab. We've got a pH of 7.48, a PCO2 of 9, and a bicarbonate of 36. Now, at first glance, yeah, it's just a bunch of numbers. But now we know how to read the story they're telling. Let's crack this thing. Step 1, you always start with the pH. Ours is 7.48. So is that higher or lower than our normal range? Right, it's high. And that tells us we've got a case of alkalosis on our hands. Okay, we know it's alkalosis. Now we have to find the cause. Let's go back to our golden rule. Metabolic equal respiratory opposite. The pH is high. Let's check our metabolic suspect, the bicarbonate. It's 36, which is also high. Look at that. They're moving in an equal direction. That points the finger straight at a metabolic problem.
So, we've got our culprit. It's a metabolic issue. Now for the final piece of the puzzle, compensation. How is the metabolic system's best friend, the respiratory system, doing? Well, the PCO2 is 9. That is way below the normal range of 35 to 45. It's definitely abnormal, which tells us one thing for sure. The friend is trying to help. And there it is, our full diagnosis. A high pH moving together with a high bicarbonate gives us metabolic alkalosis. And because the respiratory system's PCO2 is abnormal, we know it's partially compensating. Case closed. The final diagnosis is partially compensated metabolic alkalosis. So, in just a few minutes, you've learned to decode this really complex conversation that's happening inside the human body. With just 3 numbers, you uncovered a whole hidden story. It kind of makes you wonder, what other secret languages is the body speaking? Just waiting for us to figure out how to listen.